Let's have a look at the first and most common scenario, parameter exploration. So suppose you have a spreadsheet and that contains three quantities: temperature, pressure, and humidity. So basically each row of that Excel spreadsheet contains one particular situation for which you want to do a computation. So you would have to do as many independent computations as there are rows in that particular spreadsheet. And you already have a job script that is able to do a single such computation. So basically you would change the working directory to wherever you submitted your job, and then you call the application weather. We just assume that it exists and that it takes three parameters. One is the pressure, the other is the temperature, and the last one is the humidity. And basically, if you were to submit this particular job script, and if that weather application would happen to exist, some computation based on those particular values for pressure, temperature and humidity would be carried out. And then of course you want to do that for each row of your spreadsheet, so you would have many very similar computations, the only difference being that you are replacing the values for these three quantities each time. And of course that is a very common scenario. So basically we can do better than submitting that many jobs and keeping track of them. So basically this is a scenario where you do many single call computations. Okay, so Worker offers a solution for that. Basically it helps you do that in a more efficient way. So essentially we use a comma separated value file. Let's call it here for convenience data.csv, and in each column there is a quantity, temperature, pressure and humidity, and each row, except for the first one, that contains the names of the parameters, but all the other rows contain instances of our parameters for which we want to do individual computations. And then we adapt the job script a little bit. So one of the things we do is, rather than requesting a single node and a single core, we request, for instance, 5 nodes and 36 cores per node. And we also adapt the wall time. We'll discuss that later on as well. So the call to weather also changes a little bit in the sense that the actual values for pressure, temperature and humidity are replaced by bash variables with the names of the columns in the data.csv file. So the temperature column will be represented by the $temperature variable at and so on. And then rather than using qsub in order to submit our job, we use wsub with two arguments. One is the data file, so our data.csv, and the other is the PBS file, and that would just be -batch and then job.pbs. So typically in a data exploration scenario you follow the same kind of steps. You write a PBS script with parameters, so basically with names for the quantities you want to compute on. And then you create an Excel sheet with data and you convert that to CSV. Or you write a CSV file directly, depending on what you prefer. And then you submit with wsub. And of course you have to keep track of the wall time, because the wall time now is no longer the wall time required to compute a single work item, a single computation, but rather to do all n computations. So basically we assume we have n rows in our spreadsheet, so the wall time of the job will have to be larger than the total number of work items times the wall time for a work item, divided by the number of nodes times the number of cores per node which you're using. And of course, it's always safe to make the wall time for the job a bit larger than that particular fraction, because there will be a little overhead and you might underestimate the wall time of some individual work items. So let's take a concrete example, for instance, for running our computations. So R is to some extent parallelized, but it's not so very efficient in general. And if you are in a parameter exploration scenario, then actually you don't need to rely on R's parallelization. You can just use worker in order to do the job. So basically, when your computations are independent, you can actually do that. So that would be the case in parameter exploration. And here's an example. So you would write an R script with a for loop, and that for loop is ranging over tuples of two values, a and b, and then some computation happens based on a and b, and some sophisticated function of a and b is in fact computed. And there is an assumption here. Basically, our sophisticated function should take a while, and we'll quantify that later on, but it should not be something that is done in a fraction of a second. Okay, how can we adapt this R script in order to use it with worker in a parameter exploration setting? So basically the first thing to do is to pass values of a and b into our R script using command line arguments. And basically it's easy to read those in R. You just use command args, and then the first argument in that array which you get in that vector will be a. It's converted to a double precision number because args will contain strings, and the same for b. And then we do our computation. So the for loop has been taken out of the script, and the values of a and b are passed into the script through the command line. Okay, so you could run that by using R script, the name of your R script, and then the parameters you want to pass in, so 1.3, 5.7 in this particular case. Okay, so basically you can create a PBS file and a data file, and that would load a particular R module. Note, I haven't specified any R version. That's bad practice, but that keeps my slides up to date a little while longer. Also notice that there is an export omp num threads equal to 1. That ensures that R in the background won't try to do multi-threading. So basically it won't try to use multiple cores for a single computation. This is really crucial, because otherwise it might happen that you have, say, 36 instances of R running, and each of these 36 instances would try to use 36 cores, and basically all execution would crawl because you're massively oversubscribing the 36 cores in that particular machine. To run the job, load the worker module. Again, this is some version, an old one, so use the most recent version of R, of worker, and then you use wsub -batch the PBS file -data with data.csv. Another use case is for talk job arrays. So PBS talk supports job arrays, so you can submit a job script, jobarray.pbs, using qsub and using additional command line option -t from, for instance, 1 to 100. That actually means that an array of 100 jobs is submitted, so not an individual job, but actually sort of a set of 100 jobs. And each of those jobs will be individualized through the value of a variable, an environment variable, PBS array ID. So if you look at that job array.pbs file, you see that it looks as you would expect. It's a single node computation with a single core per node. And we are executing an executable CFD sim that takes an input parameter file and will generate an output result file. And the name of that input and output file, those are parameterized using that PBS array ID environment variable that is set for each array job, each job in the array, by the PBS Talk resource manager. And so essentially, you will be running quite a number of jobs where each has a particular value for PBS array ID. So it will be run once with a PBS array ID equal to 1, with PBS array ID equal to 2, up to PBS array ID equal to 100. And we can also do that with worker. It takes the same parameter -t, the same command line option. And of course we change qsub for wsub, since we want to submit this as a worker job, and we specify the same -t flag. So again, we will have 100 individual computations, and we submit the same batch job with one small change. We up the ppn to 36. So essentially now 36 work items will be run on one node simultaneously, and basically apart from that nothing changes to our job script. The advantage is that this runs as a single job rather than 100 individual array jobs.